This was our first theorem, so now we're getting back to definitions and examples. So we're going back to the soft stuff in some sense. Definition 1.13, another notion of set theory I want to introduce without using them directly, but this is what we would definitely need later. If we have two different sets, are not necessarily different, but if we have two sets M and N, then the so-called Cartesian product of M and N, by the way, the name Cartesian comes from the Latin version, Cartesius, I think, of the French philosopher René Descartes. So this doesn't have to, I mean, Cartesia sounds a bit like a country, like we're on the road to Cartesia at the moment, but this is just where this strange name comes from this guy called Cartesius in Latin. Okay, the Cartesian product of M and N is another set denoted by M times N, which is simply defined as the set of pairs x, y, which we just write in this tuple way, such that x is in M and y is in N. So just formally write them as pairs here. And more generally, if we have some number of sets M1 to Mn, then the product of these sets, we can write this as M1 times M2 times and so on times Mn. This is just a set of so-called n-tuples, and if we write this in this way, we just take x1, x2, xn, such that for all I between 1 and n, xi is an element of mi. And because this is quite long, there's a shorthand notation for this. This can be denoted by this big product sign. This is actually capital pi as a letter, as a Greek letter. The product from I equal to 1 to n, we write it in this way, mi. So this is defined like this, and this is, of course, then defined like this. So this is shorthand notation, and please get used to the shorthand notation and try to get rid of this dot notation as soon as possible, because it's just more professional in some sense and more readable when you write down your thoughts. Okay, just a quick example before we go on. If we just take M to be the set containing 1 and 2, N the set containing 0 and 1, then the product of these. So the set of pairs such that the first component is in M and the second is in N. So how many possibilities are there? Let's see. We take first, the first one is a 1, then the second one can be 0 or 1. So we have 1, 0 and 1, 1. Now we take the first component to be 2, then we again have two possibilities, 2, 0 and 2, 1, and that's it. And a very frequent example that you will already encounter in physics, of course very early, you can take R3, the Euclidean space. Now I assume that R has been constructed already, which we will do in the next sections. This would be R times R times R, and this would be, geometrically the three-dimensional Euclidean space, which is, of course, used a lot in classical mechanics, Euclidean space, so which will be in your theoretical physics course. Okay, don't want to go into details here, so so we have this definition available. Now we take another very, very fundamental definition, namely, if we have two sets, x and y, we want to define the concept of a map between two sets. So a map is denoted by f x arrow y. So we read this as f goes from x to y. So a map associates with every element of x an element of y. Associates with every x in x an element of y, and not only that, a unique element. So we do not associate 2 points to the same element or something. We just take every point in x to a point in y. And so this arrow is then giving the direction here. So a unique I don't want to write this, element of y. And we write this element then as f, and then in brackets x, f of x, we say like this. This is then the, so this is an element of y, and this is just the notation for the element associated by f with x. Okay, you've all seen this concept already. Just to take this here formally. Some notation, if we have a map from x to y. So this was part A, sorry. Part B means the space X is then called the domain of F. Y is the so-called codomain. I don't like this term, but it's the most common term in use. Codomain of F. Okay. Then again, for our bookkeeping, we need to be precise. Two maps, F, G, which goes both from x to y, are called equal. So what's this supposed to mean? And I think you already know what it means. Are equal if the following holds: f of x is equal to g of x for all x in x. Now this is an equal. I mean, we haven't said precisely what a map as an object is, so equality is not directly defined, but this is an equality of elements in y, and if we have this for every x, this means equality. Okay, D. For a set A, for a subset A of x, the following set f of A, this is just supposed to denote all the points in y, such that there exists an x in A, such that f of x is y, so x is mapped to y under f, we also say. This is a subset of y, of course. This is called the image of A under F. Okay, now we do a very similar construction. If we now take a subset of y, then we take f to the minus 1 is the notation for this, of B. This is defined as the set of all x in x which are mapped to B. This is the pre-image of B under F. Okay, yeah, this is not that exciting, but this is kind of the idea. So what everything that is mapped to a certain set in some way. We will use this frequently later on. Okay, very simple example of maps, or examples of maps. Some example you've already seen in high school would be something like this. We have a map which goes from the real numbers to the real numbers. Again, assuming that we already know what this is. F of x is x squared. So this is just this would be an example of a real function of a polynomial, so you've seen them before. Another example, we could do this in a more set theoretic thing. We take the set of all students at the University of Leipzig. And we take a map from this set to R by simply associating with every student some number, namely g of x is defined to be the height of the student x. So this would also be we associate with every guy, with every person here at the University of Leipzig a number. So this is the example of a map. Okay. Now, for bookkeeping, there's another theorem where we'll also only prove a very small part. And I encourage you to complete this by proving the rest. If we have sets and a map between those sets, x and y, a map, part A, first of all, for all subsets, A1, A2 subset of x, we have some properties concerning maps and intersections and unions, as we did before. And this is a bit tedious to write down. The image of the union of subsets is the union of the images. F of A1 union with F of A2. Part 2. The intersection does not behave as nicely. The image of the intersection, this is in general not the intersection of the images, but it's contained in, so there's a subset here, the intersection of the images. Okay, part 3. So if we take A1 and take the image of this is a subset of Y, and now we consider this and take the pre-image of this, which is again a set of X, a subset of X. So we first map this and then take it back. So how does this behave to the original set? And in general, this will also not be equal. Maybe Florian in the exercises can tell you a bit more about this. This is a subset of this set, but in general, this side can be bigger. Okay, part B. Let me just write this on this board. B for all. Now we do it the other way. With this was about images. Now we consider pre-images. For all B1, B2 subsets of Y, we obtain that first the pre-image of a union is the union of the pre-images. This also holds in this way. And secondly, the same with intersection. It behaves better. Namely, here we know that the pre-image of an intersection is in fact always the intersection of the pre-images. So this is something you should keep in mind. Pre-images always behave very, very nicely as you would hope for. Okay, and I will only prove one small part of this because this would be very dry and take a lot of time, namely the very first of these equations. Oh, Jesus, I should get a mechanic here. Anyway, so the image of a union is the union of the images. This is what we want to show. And we could go the same way as before and show that this is a subset of this and then the other way around. But here is an example of a thing where you can do this directly without the necessity for such a proof with a lot of effort. Namely, if we just write down the definitions. The image of the union of A1 and A2, this is by definition the set of all y and y such that there exists an x in the union of A1 and A2 such that f of x is equal to y. So what does this mean? Since this is the union, we can reformulate this in a very simple way. The set of all y and y such that two possibilities. There exists an x in A1 such that f of x is equal to y, or, here, logical or, there is an x in A2 such that f of x is equal to y. But if we take a look at this definition, so this is this thing or this thing. So if we take a look at what we did before, this is nothing but a union. Namely, this is the union of all y and y such that there is an x in A1 with f of x equal to y. Taking this set and taking the union of the set with the other way, the set of all y in y such that there exists an x in A2 which is mapped onto y. But if we take a look at these two sets, these are simply f of A1 and f of A2. And so we just get the union of these two. And this shows this equation. And as I said, I won't show the other relations, but they are treated similarly. Okay, let me erase the blackboard again. For the rest of the section, we will talk about some additional concepts involving maps between sets. The first, very elementary, definition 1.18. If we have three different sets, or not necessarily different, but three sets, x, y, and z, and we have one map from x to y and a map from y to z, then we can define the composition of maps. We can compose them. The composition of G and F is again a map, and then the following, the map G, and then I was indicated with a little circle between the two, G circle F, is now a map which goes from X to Z. Namely, the idea is first we associate with every X an element of Y in terms of F. Then we take this element of Y and associate with it an element of Z by using G. So we just use one after the other. And this reads as follows. This composition G circle F of an element X of X is defined as first taking the element F of X and then taking, so this is now an element of Y, and then taking G of this element. And since this ends in Y, this starts in Y, this is well defined. So this is really a vector map. So simple example, a quick example. Again, assuming that the real numbers exist. F and G are both taken maps from R to R, where f of x is x squared plus x, and g of x is simply x squared. Then g circle f of x. So this would be g of f of x. G of something is just something squared. So this would mean this is f of x squared. And f of x, we can just insert the formula. This is x squared plus x squared. And assuming we already know how to compute with real numbers, this is x to the 4 plus 2x to the 3 plus x squared. Done. Okay, so this is a notion that we will frequently need. Next thing are some important concepts which may seem a bit strange, or you might even ask, why are we doing this? And I can only tell you that these are very fundamental concepts of maps that will pop up everywhere later on, and that they are really important to formulate decisive properties later. So we take two sets and a map between these sets from X to Y, be a map. Okay, the first part is F is called injective if the following holds. Whenever we have 2 points in X which do not coincide, so with X not equal to Y, then the images under F are also not equal. So no two different points are mapped to the same point by F. F can still, after applying F, we can still distinguish the points. That's the idea here. B, F is called surjective if for all y in Y, there exists an x in X such that f of x is equal to Y. So for every Y, something is mapped onto these elements. So every element in Y is met by images of F. And C, finally, F is bijective if it is both. If it is injective and surjective. And if you think about what this means, is now first, if for all y in Y, we know that there exists an element of X, but we also know, since F is injective, that no two elements are mapped to the same point. So we know that there exists a unique X in X, which is mapped onto Y. So we cannot have two different ones. For all y in Y, there exists a unique X in X with f of x is equal to y. And this means, so we can uniquely associate points from X with points in Y, and this then shows that this is also called a one-to-one map, because it puts really the points of X and the points of Y into, or the elements of X and the elements of Y into a one-to-one relation. So for every element, there's a unique element on the other set corresponding to it. Just draw a simple diagram and then give an example. So if we have, let's say we have some x and y, and we have a map, and I denote this as an arrow, which is called f. So if we have some points in here, something. So if we have an injective map, this means that this point is mapped onto some point here, this point is mapped onto some point here, this is on some other point, but the important thing is no two different points are mapped to the same point. We can always distinguish and trace back which point we started with. So this would be injective. So same thing again, x and y. So now if it's surjective, we only know that every point here is met. So we know that there might be this point mapped onto this onto this. This might be mapped to the same point, and so on. And so for every point we can find some, but there might be multiple points which are pointing on the same thing on the other side. So here's again f. So this would be surjective. And for a bijective map, we would just know that for every point on the one side, we can find a unique point on the other side, so they really correspond nicely to each other. So here we would have maybe this onto this onto this by map f, so this is supposed to indicate a bijection. Okay, so this is just an abstract concept. Just give you a simple example of maps that have this property, these properties. Maybe I'll leave the images about here. So example 121. First of all, the map which goes from the natural numbers to the natural numbers, namely f of n, is simply n plus 1. Okay, this map is injective, since if two images coincide, so if f of n is equal to f of m, this would mean n plus 1 is equal to n plus 1, and this only holds if the 2 points were identical before. So no two different elements are mapped onto the same thing, but it's not surjective. Since, because we always add 1, there is no n in n that is mapped onto 1. So some element is not met, so it's not surjective. Okay, secondly, we take again a map G from n to n, which is defined as follows, and this is an example of how we can also write maps by defining it case-wise. We say that this is defined as n minus 1 if n is 2 or bigger, and we say that it's mapped onto 1 if n is equal to 1. This is well defined, since every number in n is, fits into a unique of these cases. So this is everything is fine here. This is not injective, because here we really have two distinct points mapped onto the same thing. Namely, g of 1 is the same as g of 2. Both are mapped onto 1, so this cannot be injective. But it's surjective, since for all n in n, we have an element mapped onto n, namely f of n plus 1 is always mapped onto n. So every n is met by f, so it's some element is put onto n. And this is what we wanted to have. So this means it's surjective. So for a bijection, I'll give you a very simple example. Let's assume we have a map from the set 1, 2, 3 onto the set A, B, C. Just saying h of 1 is A, h of 2 is B, h of 3 is C. This is bijective. Both are sets with 3 elements, so from a set perspective point of view, if we don't know what these symbols should mean, it's irrelevant which one we take. So this is really a one-to-one relationship between the first three numbers and the letters. Okay, sorry, oh yes, okay, so we will finish off this section by having a nice little theorem about bijections and bijective maps. Let me use the other blackboard because I need some space here. Theorem 122, that x and y be sets and f from x to y a bijective map. Oops, bijective map. Then there exists a unique, because I said, so this kind of identifies the two sets, and this means we can go the other way. Namely, there exists a unique map in the other direction, map G, which goes from y to x, with the following properties. G circle f of x, this is now mapped from x to x. This just maps everything onto itself for all x in x. And the same for the other composition, f circle g. This is now a map from y to x to y. So this maps every y onto y for all y in y. So these two compositions are inverting each other, as we say. Okay, this is not very surprising, but let's carry on the proof. So first of all, this is something which is really not that trivial. Uniqueness. Could there be two maps which have this property? So let's assume we have two. Assume that G1, G2 are maps from y to x, and they satisfy the first of these two properties that we want. G1 circle f of x is x, and this should also be true for G2. G2 circle f for all x and x. Okay, we need to derive that G1 and G2 are then equal. We start with G1. First of all, we take a point in y, and we need to show that on every point in y these two coincide. Since, by assumption, f is bijective, it is especially surjective. So there exists an x in x with f of x is equal to y. Okay, what does this help? This helps a lot. Namely, from this it follows. Sorry about the blackboard situation here. G1 circle f as, G1 of y is now the same as G1 of f of x. This we can write in this composition notation as G1 circle f of x. But by assumption, this now coincides with G2 circ f of x. And now we go the other way around. This is the same as G2 of f of x. And this is, of course, the same as G2 of y. Okay, we have chosen an arbitrary point, y and y. We have shown that for every point these two coincide, and this was by definition, this says that these two maps are equal. So this shows the uniqueness. The existence is not very interesting, but we need to show it anyway. Okay, here we have just assumed that there exists such a map, but we really need to ensure this by constructing this. First of all, f is bijective. So this means for all y in y, there exists a unique point which I call x with index y in x with f of xy is y. So this is unique. So since we have this uniqueness, we can use this to define the map G such that it does what we want. G from y to x, is supposed to be defined as g of y is just this element xy. Since there is only one, this is really well defined in this way. I can really associate this unique element. Okay, and one checks, and this is what I will not do, then G has this desired properties, has the desired properties. And this I ask you to check for yourself. So the desired properties, these two here, that this really inverts this construction, but this is, this fits in one line. So this is the way we can really construct such a map. And let me just conclude by destroying my blackboard ordering. I'm sorry. Just have a final remark, and I don't want to erase the board again. A final remark, 123. In the situation of this theorem, of theorem 122, we define f to the minus 1, which we have used for the pre-image notation before, but here it's supposed to be something different. This is just a different notation for this map f. So the map which has this property that it's really redoing what f has done, this is then denoted by f to the minus 1, and this is called the inverse map of f. Inverse map. Okay. Well, so much for the dry realms of set theory. I hope that you got a good first impression, and of course you might also start asking, why are we doing this actually? The idea is now we have a really good set theoretic foundation, and we want to use this now to really construct these real numbers, as I've mentioned before, and to construct numbers in general. Namely, numbers are sets, but numbers are sets with more structure. Namely, we want to have some mathematical operations like addition of real numbers, multiplication of real numbers, and so on. And so we want to formalize this. We start now with having a good foundation for sets. This is now a solid foundation that we can build on. And then we'll start to put structures on set, these computational structures. And by really slowly deriving their properties in the next section, we will then make a big step towards the construction of these sets of numbers, so to have just a solid mathematical foundation to finally get the sets of numbers we want to work with and to really do fancy mathematics with. Okay, so much for this section. See you in the next video.